I'm John Tull, the Science Coordinator for the Great Basin Landscape Conservation Cooperative. For those of you who may be new to the LCC, we're a partnership among public and private groups working to meet large-scale conservation challenges across the 5-state Great Basin region. We've supported a variety of conservation projects on high-priority topics. This webinar series highlights a few of these projects, plus additional details that our presenters choose to share. And we hope that the webinars can provide a platform for discussion about research and its application to the Great Basin. We'll keep today's presentations relatively short, about 30 minutes, and then we'll reserve the second half of the hour for questions and discussion with the presenters. Since there's a lot of people that are on the webinar, what we do is ask that you type in your questions as they arise. We'll read out your questions for the speaker at the end of the presentation. Today's webinar will be recorded and available on our website as well. So for asking your questions, what you'll notice on your screen is a small collapsed control panel in the upper right corner. If you click on that small arrow, you can expand the control panel. And in this expanded area, you'll be able to send in a question. Just type your question into the chat area itself. And then you press send. The question will show up and we'll put it in the queue for the end of the webinar. What I'd like to do now is go ahead and introduce our speakers, Bruce Wylie and Steve Boyte. Dr. Wiley earned his Bachelor of Science in Range Management from the University of Montana and his MS and PhD in Range Science from New Mexico State University. He has had his vegetation and ecology experience based in GIS, remote sensing, statistics, and the data mining of knowledge, combining all of those. Bruce has a long history of ground truthing and remote sensing mapping work in West Africa, Central Asia, the Western US, and Alaska. Mapping applications that he's used include biomass carbon fluxes, land cover, cheatgrass, and permafrost. Steve Boyte is a senior scientist with SGT, Inc., and serves as a contractor to the USGS Earth Resources Observation and Science Center. He integrates satellite data with biogeophysical data into regression tree models to map and study land change, primarily in the western US rangelands. His recent work is focused on mapping both historical and near real-time cheatgrass percent cover through much of the sagebrush ecosystem. These maps are designed to provide a better understanding of annual cheatgrass dynamics and to assist land managers and fire modelers as they seek to protect wildlife habitats and rangeland resources. In today's webinar, Bruce and Steve will discuss their recent work mapping herbaceous annual vegetation across regions in the Great Basin using high-resolution satellite data and ground observations that they scaled against moderate-resolution satellite imagery. So with that, I'll go ahead and hand it over to our presenters.
Okay, thank you very much, John. This is Steve, and I'm sitting here next to Bruce. Colin Homer is a co-author, but he is not with us today. He's out in the field collecting data, which we desperately need. Anyway, thank you very much for inviting us to speak in the webinar series. And without further ado, I'm just going to get started so we don't take up too much time. The purpose of this presentation today is to discuss the development of data sets and maps that we've created that estimate herbaceous annual cover in the sagebrush ecosystem, at least a good chunk of the sagebrush ecosystem. And we're emphasizing annual grasses, specifically cheatgrass, because it is the dominant grass in most of the area, especially in the Great Basin. We've developed basically two types of data sets. One is a near real-time data set, or data sets, and the other is a historic time series of the early herbaceous annual data. And both data sets are spatially explicit. The historic time series is designed to inform the near real-time model development and to inform science analyses. We've done work with mapping cheatgrass underperformance, also known as cheatgrass die-off in the northern Great Basin. And we've also mapped the effects of projected climate change on cheatgrass percent cover. The near real-time data sets are designed to provide a timely estimate of early herbaceous annual cover for fire planning and modeling. The data and tools that we're using, we're going to use, or we have used, multi-scale ground truth training data. This is both Eric Peterson's data from northern Nevada and the Oahe uplands, and then Colin Homer's shrub mapping group's data through much of the western United States. We use best pixel 7-day eMODIS NDVI components, or composites, excuse me. And then we also use some geophysical ancillary data like elevation data, elevation derivatives like steep slope and aspect, and then soils data, among others. We integrate all of this data into rule-based regression tree and mapping software to generate our data products. First of all, to discuss just briefly Peterson's data sets. He produced a cheatgrass map from northern Nevada that some of you may be very familiar with. It's based on both field data and 6 scenes of Landsat data from 2 dates. And this Landsat scene data was collected in 2001. It has a fairly respectable correlation coefficient of 0.71 and an RMSE of 9.1%. The Oahe uplands that map was generated in the mid-2000s, and it also used field data and Landsat data with cloud gaps filled with MODIS, and correlation coefficient wasn't quite as robust as the northern Nevada correlation coefficient, and the overall RMSE was a little lower too, with ranging from 10 to 16%. These were the 2 data sets, the spatially explicit data sets that we were familiar with and aware of. And so when we first started mapping cheatgrass in the about 2010, these are the data sets that we used. Since then, Colin Homer's shrub mapping group has started mapping herbaceous annual components across the United States, or across the western United States. And we are now using some of his data, his multi-scale field data, to inform our models. And this data that we're using in these models come from 2013, 14, and 15. I'm going to briefly go through this schematic here. I want to focus mainly and talk about the field collection that they do. They gather training data in the field at a very localized scale, and they also gather validation data at 30-meter scale, spatial scale. They bring that data, the training data, back into the lab, and they integrate it with WorldView 2 or 3 imagery, which is approximately 2-meter spatial resolution data. They take it through a modeling process, and that generates shrubland component predictions for 9 different components at 2 meters. They then spatially average that 2-meter data up to 30 meters, and that is what we use. But just to give you an idea of what else they do with their data, they take that spatially averaged data and they use it as training data to further develop shrubland component predictions at 30 meters. They also use the validation data that they pick up in the field at 30 meters to field validate their shrubland 30-meter component predictions, and they also do a cross-validation with the WorldView 2 and 3 imagery that they've spatially averaged up to 30 meters. This is their final plan map geography for the shrubgrass products. It, as you can see, covers a great deal of the western United States.
Each one of those dots is one of their high-resolution sample blocks.
Okay, they are developing these products to support numerous applications, including the BLM's Analysis, Inventory, and Monitoring project, and for our benefit, the invasives. We're using it to map cheatgrass for fire suppression, and also to develop our near real-time cheatgrass maps for our study area. The 9 components that they map are illustrated here: shrub cover, shrub height, all the way down to bare ground and litter. They produce all of these at 30 meter spatial resolution, and they are continuous values in either 1% or 1 centimeter increments. You can take, for example, the herbaceous cover, subtract out the annual cover, and get perennial herbaceous cover. So essentially, they're really offering up at least 10 components. Now, how do they go about collecting this field data? How are they measuring these field data? I know they use several different methods, but one method I think will explain how they gather that data best is where they drop a 1 meter frame in a predetermined location. And then they use ocular estimates to estimate how much of each component exists within that 1 meter frame. They then take that frame, and in each of the 4 cardinal directions, they will take another reading 5 meters away from that initial point. They then take all of those vegetation component estimates, average them together, and that becomes the estimate for that 10 square meter area. That then comes back into the lab where they extrapolate it to satellite imagery pixels in the same way. And then they get their 2 meter, they combine it with their World View 2 and 3 imagery and get their 2 meter predictions. This is an example on the right-hand side, lower right-hand side, you can see a Landsat scene with a World View 2 or 3 chip inside of it. These chips are approximately 12 to 15 kilometers square, roughly. And this is where they will collect their field plot data. In each World View 2 image, they will collect data from approximately 50 to 100 field plots. They will, as I said, take that data back into the lab, use the World View 2 imagery to make predictions. And in this case, I'm showing examples of the bare ground prediction at 2 meters and the sagebrush prediction at 2 meters for Antelope Valley in Nevada. Of course, they have these predictions for all 9 components. They then take, and as I said earlier in that flow chart, they develop, they scale it up to 30 meters and then make 30 meter predictions using Landsat data. This example I'm showing here is from a paper that they published in 2015 in a remote sensitive environment. You can see the citation at the bottom of the screen, and this is for a study area in the Great Basin. On the right-hand side, you can see the dashed lines represent the Landsat scenes that they use, and it shows a lot of overlap between these Landsat scenes. They developed a pretty revolutionary way of mosaicing these Landsat scenes, so there are very few lines that showed where the Landsat scenes were mosaic. And this scene, this picture also shows the black squares are all of the World View 2 imagery chips that they used, and they would have gone into each one of these chips and collected the 50 to 100 field data plots. And you can also see clusters of red dots scattered throughout the imagery or around the scene, and that is where they picked up their 30 meter field data. You can see that here and here and here. So they scattered around so they get a good variety of areas to validate their field data. This is a final product that they produced. It's produced at 30 meter resolution. It's an example of percent sagebrush estimate in Jordan's Craters or Jordan Craters, Oregon. As you can tell, each pixel is going to have an independent value as a continuous variable. Yes, of percent cover of sagebrush in this case, but of course they have it for all 9 components. I want to talk just briefly about their model accuracy. And this again was data that I pulled from that same article in Remote Sensing the Environment from 2015. Their model accuracy at the WorldView 2 at the 2-meter scale is very high and pretty typical. The mean absolute error is 2.3%, and the correlation coefficient is 0.92%. And this is for, I should say, this is for the herbaceous annual component from the study area that I just showed. The mean cover is about 7.3% with a standard deviation of a little over 9. The field validation up in the upper right corner here, you can see the field validation of the Landsat 8 30-meter predictions. And down in the bottom right-hand corner, you can see the cross-validation. You can see the cross-validation of the Landsat 8 30-meter data and the WorldView 2 predictions that were averaged up to 30 meters. And in both cases, I want to focus on the RMSEs because those RMSEs fall what I would consider well within the acceptable range for an RMSE of continuous variables, both right around 5%. And this is over 90 or a sample size of 90 field data sites and over 8,800 points on the WorldView 2 imagery. To round out this part of the discussion of this part of the presentation, I wanted to give you an opportunity to see some of the publications that they've produced over the past several years. If you have any interest in reading more in depth in their results and in their methods, you would read the first 2 articles listed. The bottom article is actually a manuscript that's in preparation. When that comes out, that will give you an idea of some of the other work that they're doing, because what we've shown is just a very small portion of the work they're doing, because that is what influences our work. That's the work they've done that we use to enhance our work. But they have done a lot more work that is well worth many people's review. Now I'm going to move into the work that Bruce, Wylie, and I have done over the past several years. Actually, this is over the past year or so. We initially started cheatgrass mapping, as I said, in about 2010, and we were mapping over the northern Great Basin area. We since have expanded that study area to grow. It's grown about 2.5 times to about 1.3 million square kilometers. And again, just to remind you, we're mapping spatially explicit near real-time herbaceous annual and a historic time series of herbaceous annual vegetation. Okay, we want to show you how our data connects with the Homer data, and it's pretty simple. We use the spatially averaged WorldView 2 data that they generate. And we use this data as training data. We take it, we scale it up to 250 meters, and we use it as training data for our models. And that is right up here in the middle top in this red box. So Homer's data we use approximately 25,000 of their pixels as training data, and we add in about 8,000 pixels from Peterson's 2 years of work.
And you're talking about 250 meter pixels.
Yes, these are 250 meter pixels. Now, one of the things that we do is we try to use we do use a phenology approach. We want to take advantage of the understanding that we have of cheatgrass phenology, where it greens up earlier than most other vegetation in its area, and then it senesces and cures earlier than most other vegetation. And so what we're trying to do is find a difference, be able to differentiate between the remote sensing or the satellite NDVI signals between the vegetation types. So one of the things we do is we develop a start of season week, which is a spatially dynamic data set that tells us, okay, this is, if this pixel has cheatgrass in it, it's going to start greening up during this week. And we have that for every pixel in the study area, and then we take the NDVI value from that day, that first week, and we extend it out 8 or 9 weeks, and we take an average value of all those 8 or 9 values. That becomes what we call our spring growing season NDVI, or annual spring GSN. We also take and develop another spatially dynamic data set. That's our annual summer integration right over here. And that's where we look at the NDVI signal from the middle of June to the middle of July. And again, we take an average of those values, those 5 values, and that becomes our summer integration data set. We also take those 2 data sets down here and create an annual index where we take the spring GSN and the summer, and we subtract it and then divide it by GSN plus the summer. These become satellite derivatives. These are phenological satellite derivatives that we develop for each year. We also, for independent variables in our model, use topographic variables, 30-year climate variables that we get from the PRISM data set, out of Oregon State University. We use a time since fire data set, some soils data sets from Polaris, and then the 2011 National Land Cover data set. One of the things I want to make clear is we only use the time since fire data set in our historic model. We don't have that data in time to use it in a near real-time model. So one of the things you have to know is that the satellite derivatives are we only use those in the model from the training data years, and the same goes for the time since fire. Only from the training data years can we use those in the model development. So this data, along with the training and test, the training data goes in the regression tree model. It generates model rules and algorithms, which we then input into our mapping application, along with these same data sets, these same independent variables. These are spatially explicit data sets that are used then, along with these rules and algorithms, to map our data sets and map products. Okay, this is the training data footprint. The green area is data where we gathered data from Peterson's Oahe Uplands data set. The black area shows where we got his data from the Northern Nevada data set. And then the orange data, or chips, that's where we used Homer's subgroup data sets. And we focused our training on areas of cheatgrass or annual grass with a 30% threshold or greater. So it had to have 30% or more cheatgrass, or we did not train on the pixel. Anyway, 250 MODIS NDVI. I know some of you, probably all of you, know what cheatgrass looks like, what the annual grasses are in your area, but you may or may not understand the value of NDVI. We use enhanced moderate resolution imaging spectral radiometer, or radiometer normalized difference vegetation index data. These are daily MODIS acquisitions that are processed into 7-day best pixel NDVI composites, as I said earlier, and they're available in weekly time steps. This allows, with the daily acquisition and the weekly time steps, allows the data to capture rapidly developing and changing vegetation dynamics. We also apply a temporal smoother that helps to remove residual cloud cover effects. Right there you have the NDVI algorithm that produces the NDVI values that have been used as a proxy for vegetation dynamics to map biomass as a proxy for net primary production and to differentiate between vegetation types, as we're doing here. This is another example, or really quickly I want to go through this. This explains or illustrates how we try to use the Cheatgrass phenology NDVI signal and differentiate it from, for example, in this case, a big sage signal. In the early spring of the year, you can see that there is a distinct separation between these two profiles, and that's where we intend to target our collection of the MODIS NDVI growing season data, and that's where we average the data, and then that will separate the spring growing season NDVI for cheatgrass from other vegetation types. To further illustrate, on the left here, this is an example of a spring growing season NDVI data set. Areas where it's bright, that's areas where we would expect to have vegetation greenness early in the spring. The summer GSN is areas where it's bright, is where vegetation would be green and growing and most active in the summertime. Typically, those are not going to be areas that are bright in the spring. So areas that are bright in the spring, dark in the summer, are potentially areas of cheatgrass or annual grass growth or invasion. And this is an example of our annual index. So each of these three data sets are developed every year on an annual basis, and they are used as dynamic variables in our modeling process. This is the first of about 5 maps that I'm going to show you that are basically our results. This here is the 16-year average, and it shows quite a bit of growth of cheatgrass percent cover in the Snake River Plain, in the Winnemucca, Nevada area, over here on the eastern edge in Wyoming, and a little bit in South Dakota and North Nebraska. And one of the things when we model is we want to focus on our mean absolute errors that our regression tree model produces, and we want to make sure that we don't overfit or underfit our models. And so we want those mean absolute errors from the training and the test data to be close. We can improve our correlation coefficients if we aren't concerned with this mean absolute error, but we want it to remain close to minimize over and underfitting. And in this case, we've gotten very close with this annual or with the historic model. The top 5 variables that were used in here, this is the average usage between the rule stratification in our models and the actual algorithm development of the model. And so the spring growing season NDVI and the elevation independent variables were used most frequently in the development of our model. The PRISM data sets were the next 3 most often used in this historic model. Now I want to move to the early estimate. This is a data set that we stopped using MODIS NDVI data on April 28th. Okay, so basically this is about the May 1st, 2017 early estimate of herbaceous annual cover. You can see higher than average cheatgrass or annual grass percent cover in the Snake River Plain and in the Winnemucca, northern Nevada area. Again, looking at the training and test mean absolute errors, we show very close error rates. And so again, we're not concerned about over or under fitting. And the correlation coefficients, are again fairly substantial. Over 9 randomizations, our standard deviation was plus or minus 0.15, which indicates a very stable model. One of the new variables that we input into the near real-time model is we took the 16-year mean, and that became one of our independent variables. It was used by far more often than any other variable. When we go to our next June 19 near real-time estimate of herbaceous annual cover, this is where we used our MODIS NDVI data through the 19th of June. We get a similar map, but some of the values in the Snake River Plain and in that Winnemucca area where we're generally seeing high values of herbaceous annual cover, it's a little muted from the May 1st map, but it's still greater. The percent cover is greater than the 16-year average. So our estimate is that 2017 was a better year than average for annual grass percent cover in these areas. The last, or the second to last map that I want to show you, this is we took the May 1st early estimate and we created a difference map from the 16-year mean. Areas that are red are areas where there's at least 10% more than average annual grass cover than you would get from the 16-year mean. And there's a few areas where there's actually less cover, and that is illustrated by these green areas here in East Central California, Southern Nevada, and then just a small number of pixels in the Western Snake River Plain. But for the most part, the areas that have changed from average or significantly from average are in the Snake River Plain and the Winnemucca, Nevada area. Overall, though, the mean change is minus 0.11%. So basically, overall, there would be statistically no real change. Finally, I want to show you a difference map that we zoomed in on. And this is right around the Winnemucca, Nevada area, just to give you an idea of how much change took place this year in that area. Quite a bit of this area shows 10% or greater change, increase in percent cover. And there's even a lot of lighter blue colors that indicate up to probably somewhere between 5 to 10% increase in annual grass cover. Finally, I want to allow you guys, give you the DOI numbers so that if you choose to, you can access the data, the early estimates of the herbaceous annual cover and the near real-time herbaceous annual cover from 2017. Later, as I said earlier, I believe in probably about mid-September of this year, we should be releasing on ScienceBase as well the historic time series from 2000 to 2016. If you don't have time to write down these DOI numbers, you can go to the ScienceBase page and just search for my last name, and these data sets will probably pop up at the top of the screen. Future plans for this work. As I just said, we're going to develop and publicly release the historic time series of the herbaceous annual cover maps by middle of September, hopefully. We're also going to develop some validation data sets for the herbaceous annual cover. The plan is to develop and then publish a manuscript that is going to discuss that validation of the annual cover data set. Another one that we're going to work on is we're going to use the herbaceous annual cover data to develop ecosystem performance anomalies. Now, this is a technique that we've used in the past to map, for example, cheatgrass die-off. What this technique does is it separates management actions and disturbances from the climate signal. So what you do is you get more interpretable results. You're not muddling the climate signal with other activities that are taking place or other actions that are taking place on the landscape. We also are going to then develop and publish a manuscript outlining that work, and then we will continue with the development and the release of herbaceous annual early estimates. in 2018. Finally, we're working, I think, Bruce, are we working on a contract or are we finalizing a contract?
It's in the process.
Okay. To downscale the 250 herbaceous annual cover to 30 meters using Landsat data, and we're supposed to be doing that in several forest or Fish and Wildlife Service national wildlife refuge areas. Finally, we would like to acknowledge our funders, including the Great Basin Landscape Conservation Cooperative, and also again thank them for the opportunity to present today. And we'd like to acknowledge USGS Land Change Science and the Bureau of Land Management.
Thank you, Steve and Bruce. That's a really informative talk. There's obviously a lot of complexity that goes into creating models that provide this really useful near real-time type information. I think we've got questions that are starting to come in. I want to remind people, if you have questions, go to your control panel and then drop down the question area if it's closed, and then go ahead and type your question in there, and we'll relay it. And so I just wanted to start off with one question on my own here. And I was wondering if you guys have any examples of the application of your products, particularly in light of the fire season we've had, if there's been anything that you know of that where these products were used to help prioritize either on-the-ground activities in advance of fires or reactions post-fire.
This is Bruce. Not exactly, but yesterday there was some email from the land fire program members that they wanted our historical data sets to include in their analysis. So I think they were looking at those data, but per se I can't say of any exact application for fire, although there's been strong interest. I will say that one of our BLM collaborators looked at our data, compared it to 2016 AIM plots from the BLM, and was favorably impressed. Some areas of slight overestimation and others of slight underestimation, but generally a pretty positive feedback from using the BLM AIM plot. Any other applications you can think of, Steve?
Well, I can't think of any applications, but I can say that we started to develop these near real-time data sets in response to some interest. We had people say, hey, you know, these historical time series are great, but if you could get these out a little earlier, that would be great. So we had to go back to the drawing board and figure out how we were going to develop near real-time data sets. So in 2015 and 2016, in the northern Great Basin area, we were able to develop them and get them produced by early July. And then earlier this year, we had requests or people saying, hey, if you could get these out even earlier, that would be useful as well. And maybe we could use it in our fire models, and the land managers could use them in their fire planning. And so that's why what we did, we went back to the drawing board again, modified our inputs a little bit more, and that's when we were able to produce the data sets by mid-May. And hopefully we might even be able to get them out a little earlier in subsequent years. I think that the data may be getting traction, but I think it's really kind of early to tell. We haven't got any feedback. So if anybody knows of anybody that's using it, it would be great to hear how they used it and what they thought about it.
You know, the LCC money came from Rick Carney, and he's developing a decision support system for the Great Basin LCC. So as soon as we got those out, we definitely shipped those off to him right away. I don't know how far along his decision support model is, but that's another potential application user.
Great, thank you guys. So I'm here monitoring our question inbox, and we've got quite a few that just came in the last few minutes, and one or two from earlier in the presentation. So I'm going to start reading through a few of these for you guys. And the first question that we have here is, how do you determine annual spring GSN?
Okay, you want to do it, Bruce?
Well, let me try first. We have a phenological product called start of season that is determined from that weekly NDVI time signal. It's a product where they estimate when the start of season begins. We've done a lot of work comparing with our historical data set and looking at when that start of season actually produced a sustained growth for cheatgrass. And so Steve, one of his papers is about developing that kind of conversion of start of season from the phenology metrics to the sustained week for cheatgrass. But that gives us a temporally and spatially varying start of season when we do our integration. Our integration is not a calendar date. It varies with elevation and the NDVI signal of that year. So it's very dynamic when we do that growing season NDVI calculation. I'll let Steve.
No, I think that explains it pretty well. It's that start of season week that, as I said in the presentation, that's where we start aggregating our MODIS NDVI and get that spring GSN value.
Great, thank you guys. And if there are any follow-up questions from the audience, please just continue to send those in.
Could I say one more thing? That when we switched from a static start of season time to a dynamic varying start of season time, the accuracy of our models went up.
Okay, great. So a next question here from the audience is that I noticed forested areas were excluded. What is the criteria? Elevation, PPT, or canopy cover variable, or some other variable?
I'm sorry, I forgot to mention this in the presentation. When we mask our data using two criteria. First, we looked at the 2011 National Land Cover data set. Any areas that were not designated or classified as grassland, herbaceous, or shrubland was masked out. And that's at a basically 70, it had to be 70% grassland or 70% shrubland. And if it wasn't, then it was masked out. The other criteria that we used was elevation. Any elevation above 2,250 meters, that also was masked out.
So the NLCD is at 30 meters. So you have to think of how many 30-meter pixels are within a 250-meter pixel. That's how we get the 70% threshold. So it counts as rangeland if it's either shrub or grass. So if 70% of that 250-meter pixel is rangeland, then we map it.
Okay, great. And these next two questions here both kind of relate to teasing out different species when you're looking at the data. So in the first one here, can you talk a little bit about how you tease Sandberg's bluegrass cover out from cheatgrass cover in this area?
Yeah, that's a good question. Take that one, Bruce.
I think the answer is that we really don't. I mean, there's a very subtle difference between the signal of Sandberg's and cheatgrass. However, some people have told me they've seen this, but Sandberg, typically I've seen it as little small tufts here and there, and I've never seen Sandberg at a high percent cover. But other people from the field have corrected me on that, but it's I've never seen it. It's kind of like, Wolverine. I've never seen it. I think it's fairly rare on the landscape, high covers of Sandberg. you like to add more?
Well, I mean, this is just kind of anecdotal, but not completely. But I think Stephen Link and Janelle Downs and one other person produced a publication back in the 90s, and they were studying the difference between Sandberg's bluegrass and cheatgrass in eastern Washington. And they thought that the Sandberg's bluegrass phenology was occurred a little sooner. The growth cycle started a little sooner. So again, that's in a geographic area outside of ours for the most part, or completely. But yeah, it is an issue. And of course, talking to our BLM collaborator, you know, they're going to have different fire behaviors. So that is something that we might want to see if we can tease out the difference between the Sandberg's bluegrass and the Roma pictorum.
Yeah, that BLM collaborator recommended possibly looking at ecological site characteristics from the Surgo data as a way to identify areas that may be more prone to Sandberg.
Okay, thank you guys. And then kind of related here is a follow-up question of, is there any possibility of teasing these cheatgrass values out of lightly forested locations kind of on the margins of the Great Basin?
Well, optimistically, yes, as long as the canopy cover is low for the tree cover. But it would take some testing and probably almost a separate model to deal with these more mixed pixel kind of things. So, I mean, it's not a slam dunk. We actually map every bloody pixel out there, and our masking for the rangeland and elevation thresholds occurs after that. So we actually do have estimates there. What we're worried about is that we're kind of extrapolating to all of our training data came from rangeland, so we're not sure how well it's going to behave there. I think we could share that data with somebody if they have data of cheatgrass in these kind of open forest communities that would like to look at it. But we're nervous about it, and I would think that it might almost require a separate model to deal with these mixed pixel kinds of things. Anyway, anything you'd like to add, Steve?
No, I think that covers it.
Okay, great. Thank you guys. Lots of questions are coming in, so I'm going to try and get through as many of these as we can. And if for some reason we don't get to all the questions, we will send those to you guys to follow up with if there's additional information. So next one here is someone is curious about the model parameters and if those are going to be published or available, and same for kind of the software and the rules that are used.
I don't know that we have any plans to publish them. However, if somebody wants them, they can just request them, and I would be happy to send the model files and the output files. We're more than willing to share those.
Yeah, and in some of our earlier publications, we've identified the variables that we've used in the past. I would say that the model that we used is called Cubist, and it's from ruralquest.com, and they have a GNU version of the code, and is that the one that we used? Did you 2.07?
No, I used 2.08.
So it's got a free version of it is also included in R. So it's really, well, I like it. It has its criteria that it makes the rules is based on the mean absolute error, so that you're not looking at the distance squared. So this mitigates the impact of outliers. So that mean absolute error divided by the number of parameters. So it automatically tries to use the minimum number of parameters and is not hopelessly driven to try and fit outliers. It's naturally very resistant to overfitting, but not immune. So yeah, and it produces, it's completely transparent. An ASCII file comes out with every single rule, what the parameters were used to stratify out that rule, the regression equation with each of the parameters and their coefficients, and the number of observations that came into that rule, and the mean absolute error of that regression equation. So, I mean, you can, it's completely, it's not a black box. You can go in there and look and dig. You can map out geographically one particular rule or several rules on a spatially.
Thank you. So this next question is a little bit long, and I can repeat parts of it if you need. But the first part is, does the presence of Medusa head cause overestimation of cheatgrass when using the GSN techniques? And the commenter goes on to say, you know, they've observed sites where Medusa and cheatgrass coexist and where each annual occurs independently, especially within areas of northeastern California. So does this model represent invasive annual grasses as a whole, or is it NDVI technologies, you know, able to separate out cheatgrass from other early emerging grasses such as Medusa head?
Well, yeah, that's why we changed it to annual herbaceous instead of cheatgrass. We're mapping annual herbaceous grasses and forbs, and yes, you know, Medusa head would cause a false indication. Well, if you're looking for cheatgrass, sometimes we call it cheatgrass just because, you know, the bulk of the annual grass signal, you know, that early green up and then crash to senescent die signal is cheatgrass in this environment, and you know, the fire behavior is somewhat similar, I suppose. So it's, yeah, we don't pretend that we're just mapping cheatgrass. You know, we acknowledge that we're mapping primarily annual herbaceous vegetation. Could be some annual mustards in there as well. And there is going to be some overlap with Sandberg. So we're not pulling out a particular species. I guess it's more that phenological signal where early green up and then crash to nothing. So it would be, yeah, we're not trying to separate anything beyond that kind of herbaceous annual, given the phenological approach that we're using.
Okay, thank you guys. There's 2 more questions here, and we've got about 5 minutes left of the webinar, so let's see if we can get through these 2. The first one is there a way to apply this to determine forb cover instead of grass cover?
This would be a whole new model.
Boy, I mean, the forb cover, you would expect a much stronger infrared signal, but again, I think we're trying to split hairs here beyond what we can do with the MODIS satellite, and just phenologically. You know, maybe that would require hyperspectral data or high resolution data. You know, and possibly, you know, something with the near red edge signal, like the Sentinel satellite. Again, this is kind of splitting hairs, and it would require rigorous localized study to be able to do that, I feel like.
Okay, thank you. And then here, the last question that we've received so far is, can you speak a bit more about the time since last fire variable? What data set was used, and did it play a large or small role in the model?
The time since fire data set was generated from MTBS, or Monitoring Trends and Burn Severity data set. We went back, I think it was 5 or 8 years before the start of our time series, so went back into the mid to early 90s and generated time since fire, 5 years, 6 years before 2000, so we could include that. Of course, by 2016, we didn't have, because the MTBS data comes out about a year and a half, 2 years after. We weren't able to use that. We used the 2015 data and the 2016 development. But I can't. What was the second half of the question, Liz?
They were just asking if it played a large or small role in the models.
That's right. I would say more of a moderate role. If I remember correctly, it was used in about 10 to 15% of the rules development of the model, and then at about 30% of the algorithms that were used to develop the model. So I would say more of a moderate role.
But as I recall, Steve, when you ignored that variable, the accuracy of the model did not go down much. Is that right?
No, I don't think it went down much. But I think, well, no, I don't think it went down much. And of course, when we did not use it in the near real-time models, our model accuracy did not go down either.
Great, thank you both. Well, at this point, we have gotten through all of the questions that came in from the audience, and we're just about at the end of our time. So I'd like to turn it back over to John just to say a few kind of closing words here.
Well, thanks again, both Bruce and Steve, for sharing your presentation, your research, your work. And I want to thank everybody who's attended the webinar today. A recording of the presentation will be on our website later this week. And if you have any questions about either the Great Basin LCC or this particular presentation or the research, go ahead and contact me, and I'll do what I can to address your question or pass it along, or contact Bruce or Stephen directly. And you can see our contact information on the screen. Last but not least, we really want to know what you thought of today's webinar, so please take our short 2-minute survey that will appear on your screen as you log off. Your feedback is really useful and valuable to us, and it helps us plan and improve our future webinars. Again, thank you all for attending, and we'll see you next time.
Thank you.